Please note in the upcoming lecture that I write down the kinetic energy 1/2 mv squared turns into electric potential energy, which is kq1q2 over r. But accidentally, I put an r squared there. I correct it at the end, but if you know that before you start, probably helps that the r squared should be an r. Okay, so in our previous lecture, we found that J.J. Thomson's discovery of the electron got him to come up with the plum pudding model, because they of course knew that the atom was neutral, and so not lacking any other knowledge, knowing that the electron was a negative charge, that the rest of the positive charge that therefore makes the atom neutral must be spread out throughout the atom. And then it was Rutherford's experiment starting in 1909. Now, often when I state a year, I may be off by one, not really off by one, but by one compared to what you read in a book or see on the internet, because these experiments take longer than a day. And so Rutherford actually discovered the nucleus in 1909, and his famous paper was published in 1911. So 1910, you could call it 1911, Rutherford discovered the nucleus. Well, he discovered it in 1909. Doesn't matter. You get it. So the famous paper was published in 1911, where he describes his scattering theory and his theory of the hard small nucleus. So Rutherford discovered this nucleus. How did he do that? Rutherford was doing some scattering experiments. And what is scattering? Scattering is, we've already discussed scattering. Scattering is simply where you bombard one kind of particle with another kind of particle and see what comes out. That's all. It's scattering. It's throwing ping pong balls at a wall and seeing where they bounce. Or throwing ping pong balls at a piece of tinfoil and seeing if they go through or if they bounce or if they get deflected. Scattering. And so we're going to spend some time talking about Rutherford's scattering experiment and his scattering theory. But first, let's actually talk about Rutherford's discovery. What Rutherford's discovery is that he had what was known as an alpha particle source. Alpha particles. And alpha particles wasn't understood when Rutherford did this experiment what alpha particles were, because they themselves are helium nuclei, but they were understood to be heavy particles. That's what was understood. They are heavy particles. And it was understood that, for example, hydrogen atoms were lighter than alpha particles. And so if you shot an alpha particle at a hydrogen atom, the alpha particle would barely be deflected. Things like that were understood at the time. So Rutherford had these alpha particles, and he did scattering experiments of various sorts. But anyway, the one that's important is he was scattering alpha particles. He was shooting them at gold foil. And typically, when you shoot a heavy particle at something, at anything, you might expect it's going to get deflected some. And indeed, what they generally saw was that alpha particles would go straight through, and they had a detector that went all the way around the gold foil, and they would see some alpha particles get deflected in various directions, depending on now that we know, depending on how close it got to a nucleus of the gold foil, and most of the particles traveled right through with little deflection. But Rutherford, being the scientist that he was, I don't think you could make these major discoveries and win Nobel Prizes if you were not exceptional scientists. He understood that it was probably worthwhile to check all the way around the apparatus to see what was going on. It was fully expected that there was absolutely no reason that an alpha particle should bounce back back from the gold foil. The alpha particles, heavy particles, it's like throwing steel balls at tin foil, right? You expect they're so much heavier than the tin foil, they will never get reflected back. But in these experiments, we have this, and basically it's a pretty straightforward experiment. I drew this as a dotted line, but you have a material which you surround this experiment with, which lights up. It actually, it's like a phosphorescent screen. It lights up when an alpha particle hits it. So you can see, you know that the alpha particles would typically, more often than not, travel straight through along this axis, and you're going to see the most lighting up there, but you see every once in a while you see a flash there, and every once in a while you see a flash there. And this is scattering, right? The alpha particles are getting scattered off the gold foil. But in doing this experiment carefully, every so often, and very infrequently, but every so often, they would see a flash there or a flash there, right? They would see flashes on the wrong side of the gold foil. And so what was happening, and was not understood when it was happening, was that every once in a while, an alpha particle would get bounced back. How do I draw that? An alpha particle would get bounced back. An alpha particle would get bounced back. And the only conclusion that Rutherford could come to from this experiment is that there was something very small and very dense, very heavy in the gold foil. What does that mean? Well, it had to be very small because almost all of the alpha particles traveled through. It was very unusual, but every once in a while an alpha particle would bounce back. So it was almost all of them went through, and every once in a while one would bounce back. It was like, I can't remember, 1 in 1,000 or something like that. Conclusion was that the gold foil had to have been made up of mostly empty space or very light particles, such as electrons, and then largely spaced out very heavy particles. And so that led Rutherford to conclude that atoms are not the plum pudding style, but atoms are instead this orbit, this classical orbit style, where most of the mass of the atom is as a tiny little thing in the center, and the atom basically is mostly empty space. That was Rutherford's conclusion to this experiment. So it's the nuclear model of the atom. So, the nuclear model of the atom, atoms have a tiny, dense nucleus, and the atom is otherwise empty space. The light, not light as in electromagnetic, but the small mass electrons hang out in that empty space. They don't really interact with these alpha particles, because they're incredibly small and light, much less mass. And the rate at which the alpha particles bounced back allowed Rutherford actually to figure out that the nucleus was not greater than, but smaller than, that the radius of the nucleus was smaller than 10 to the minus 14th meters. He was actually able to be that specific, which he's right. The nuclei tend to be around 10 to the minus 15, 10 to the minus 14 meters. And that's what he was able to measure from this experiment. The other thing is that the nucleus, remember, the positive charge has to be somewhere because atoms are typically neutral, and so the nucleus is holding the positive charge. So it was all the positive charge is at the center. So this is the model, the Rutherford model, right? All the positive charge is at the center, and then you've got these little electrons which are in the space around it, and the atom, might be that big. And the nucleus might be, well, actually the nucleus would be a lot smaller. The radius of an atom is around 10 to the minus 10 meters, and the radius of a nucleus is around 10 to the minus 14, 10 to the minus 15 meters, depending on which size nucleus. They're talking about a helium atom or a uranium atom. Just writing some things down, the nucleus has a large mass, but it's got the same charge as the electrons, positive charge, right? The electrons are negative. So the charge of the nucleus is written as some integer multiple of the charge of an electron. So Z is an integer and E is positive 1.6 10 to the minus 19. So this is our Rutherford's model, classical model of the atom. So let's look a little closer at the physics here. Rutherford is shooting alpha particles. He's shooting alpha particles at these gold nuclei, or it could be any nucleus. And let's just imagine you've got an an alpha particle, and it's got a certain mass and it's got a certain velocity. We can call it V alpha, and it's mass alpha. And we're shooting it at this unknown nucleus, which we're just going to call it's an unknown nucleus. So we'll just say it has a charge. We'll identify it with Z times E. The alpha particle has a mass, m alpha. It's got a charge, Z alpha E. The alpha particle was understood to be a multiple of E charge as well. That says Z alpha E. It has a speed V alpha, and we're shooting it at this unknown nucleus, which has a charge ZE and a radius R we'll call it nucleus, R nucleus. And just ask, okay, so we know what Rutherford was able to determine is that the nucleus could stop the alpha particle entirely. What do I mean by that? Well, if the alpha particle can bounce back 180 degrees, which he was able to see, it could bounce back 180 degrees, that means that the alpha particle had to come to a stop, right, somewhere here before it turned around and came back. So let's look at an energy, right, so it was going in that direction, comes to a stop, turns around, and comes back. So think about an energy conservation point of view. So what is stopping the alpha particle? Well, you could say it's a hard body interaction like a pool ball on pool ball, but that's not what's stopping the interaction. What's stopping the alpha particle is the electromagnetic repulsion. Right? So what's the energy? The energy of the alpha particle is simply, at least classically, I don't think we need to worry about the relativistic effects here. The alpha particles aren't going that fast. But we can, think about relativistic effects if we need to, obviously. But the kinetic energy of the alpha particle is 1/2 mv squared. And when the alpha particle comes to a stop, what's its kinetic energy? It's 0. And where did that energy go? It went entirely to electric potential energy. Do you remember what electric potential energy is? Electric potential energy is K Q1 Q2 over R squared, where R is the distance between the two particles, really between the two particles' center. So we've got this, and we can learn something about the nucleus from this, right? So let's pretend we didn't know anything about the nucleus. All we know is that it's got some charge ZE. So we can learn something about the nucleus if we know about the alpha. And what we can therefore write, we can rewrite this equation. We can write this, and again, we know everything about the alpha, we just don't know about the nucleus. And so therefore, what we can do is we can increase the energy of the alpha, right? Increase the initial energy of the alpha. And we keep on increasing the initial energy of the alpha until we get closer and closer and closer. And again, how do we know we're getting closer and closer and closer? Let's say the energy isn't enough to get too close, so that the alpha, and let's just say that's the alpha and this is the unknown. The alpha just gets to there and then it turns around and goes back in the other direction, right? And so that's R min. That's the distance of closest approach between their centers. So then we say, oh, okay, well, we should be able to increase the energy more so we can get closer, right? Increase the energy more so we can get closer. How do we know when, and so this is one of the things that Rutherford had to figure out, is how do we know when we get so close that we maybe just touch, and if we get any closer, what we're going to do is we're literally going to have to knock this one out of its place, right? We're going to have to knock the unknown out of its place. And that is basically what comes next is scattering theory. What Rutherford was able to realize is that the scattering theory stops working when you start knocking the nuclei out of their places. Scattering theory depends on the nuclei staying in place. So as long as the scattering theory works, then he knows he hasn't gotten too close. So he increases the energy of the alphas until scattering theory stops working, and then he knows he's at the closest approach. And that is what allows him to determine that minimum closest approach, and that gives him an upper bound on the size of the nucleus. So that is the upper bound on the size of the nucleus. That's why he knows that the size of the nucleus is less than 10 to the minus 14 meters, because he goes ahead and plugs in all his numbers. Let's do a real quick, simple example. Right, we know, and I didn't say earlier, we know that Z alpha is 2. The number of the charge of the alpha particle is 2e, and the charge of the aluminum particle is 13e, of the aluminum atom, sorry, I say particle, aluminum atom is 13. And let's say that Rutherford does this experiment and finds that the energy of the alpha particle above which scattering theory no longer works is 7.7 MeV. Before we can go ahead and plug in and find the distance of closest approach. Showing, making sure we understand how to plug in, that the energy of the alpha just goes on the left-hand side. K, oh, it's K. This is not Boltzmann's constant. This is not the spring constant, right? This is the potential energy, the electric potential energy. K is 1 over 4 pi epsilon naught, remember? K is 1 over, or you can just look up K itself, but it's that constant that goes in front of Coulomb's law, 1 over 4 pi epsilon 0. And K is 9 times 10 to the 9th in MKS units. 9 times 10 to the 9th joule meter squared per Coulomb squared. That's the MKS units. Just plugging in ZE times ZE. So the two Z's are 2 and 13, and that gives us E squared, where remember E is 1.6 times 10 to the 19th, but we don't need to turn it into 1.6 times 10 to the 19th because, well, let's just go ahead and plug in. We'll see. Hold on. Okay, I just realized when I was plugging in numbers that we do have to plug in E because K we had in MKS units, and the Coulomb squared needs to cancel with those Coulomb squared. So I do need to plug in the E. If I had put K in the right units, we wouldn't have had to. But anyway, okay, so you got 1.6 times 10 to the minus 19th coulombs squared. So I realize now that my units aren't working out. And that is because I wrote down something wrong from the beginning. I did the same thing that it would be very easy for you to do. And rather than me redoing the lecture, it's easy to fix, but it's really important. And that is simply me writing down this potential energy function. This is not a potential energy function. This is the force between two charged particles. It's not the potential energy function. This is the force between two charged particles, and I wasn't being careful. Right? The force between two charged particles is kqqq over r squared, and the work done is the integral of f dot dr, and so therefore, which is also equal to the potential energy, or the change in potential energy, which is equal to minus kqqq over r. So the potential energy, oops, work is minus potential energy, sorry. Oh, I might have, yeah, sorry, messing up my minus signs, yeah. But in any case, the potential energy is between two charged particles is, I did mess up that minus sign, kqqq over r. So go back, cross out that squared, kqqq over r is the potential energy, kqqq over r squared is the force. And then there might be a minus sign depending on the charges and such, but this is just magnitudes here, right? It's the magnitude of the kinetic energy is turning into the magnitude of the potential energy. These signs are correct anyway here. Kqqq over r, and therefore I had written down the units of K incorrectly. It's newtons meters squared, and that's where I messed up, is the units of K. Newton meter squared per Coulomb squared. A Newton meter is a joule. A Newton meter is a joule. So all I have to do here is, cross out that, and cross out that. And then I get the right answer. Then I get the right answer and the right units. Understand that the units still cancel correctly here because a Newton meter, I know this is a Newton meter squared, but a Newton meter is a joule. So that does cancel out with one of these meters and the newtons there. Okay. So this still gives us, now it gives us the right answer. Before it didn't, which is why I paused, but now it gives us the right answer with the numbers that we'd already plugged in. It tells us the distance of closest approach between the two centers of the alpha particle and the nucleus is 5 times 10 to the minus 15 meters. So that gives us an upper bound on the size of on the radius of the nucleus. We know it must be smaller than that. Ta-da! Sorry about the error, but okay, good.